Lithium-ions battery is probably nowadays one of the most interesting type of battery, especially in all that portable application has smartphone. But we can even able to see these types of devices in other types of situations, as for instance inside the Stark in Tesla motors. So basically it's important to say that lithium-ion batteries represent one of the most extremely used battery, even if the price is not so limited. And this is due to the extremely interesting output voltage that these batteries can provide, and even the quite high energetic densities and long life. So basically, if we want to describe lithium-ion batteries, we need to say that this battery is based on an intercalation and the intercalation process of lithium cations. So in order to understand the working principle and also the main important aspect, positive aspect and negative one, we need to start from the galvanic change and the real structure of this battery. So the cell is composed in this way. We have obviously a negative electrode, we have an electrolyte, and we have a positive electrode. The negative electrode is composed as carbonous material. It could be just amorphous carbon materials or graphite often. So we can say that this is composed as graphite, having this well-known hexagonal layer shape. So different steps of layer of graphite. Why graphite? Because graphite exhibits a certain conductivity and at the same time are able to promote the intercalation inside this structure of lithium cation. So basically we can say that the negative electrode is composed of graphite of other carbonous amorphous materials having a nice surface area able to promote the intercalation of lithium cation, lithium plus, lithium plus. But inside this electrode, the lithium is acting as a lithium-0 as oxidation number. So even if inside this structure the lithium is present as intercalated lithium plus, is behaving as lithium-0, since the positive charge is completely balanced due to the presence of delocalized electrons inside the graphite. This is not metallic zinc. It's not lithium-0 as metallic zinc, but is acting as lithium-0 even if we are looking for a situation in which ions are present. So we have intercalated lithium-ions as lithium plus inside the graphite, and this positive charge is balanced with the electron delocalized on the graphite, and so the lithium is acting as lithium-0. So basically this is what happened on negative electrode, and we have some oxide, lithium oxide, we will see which types of lithium oxide on the positive electrode. And we have our electrolyte. We will see later what is the types of electrolytes used and even the types of lithium oxide electrolyte. The reasons for which lithium-ion batteries are so interesting are a lot. First, the possibility to intercalate lithium inside a graphite support is extremely useful in order to achieve a high output voltage. And so a quite high power of these batteries is achieved. And this is due to the fact that basically lithium is an extremely strong reducing agent. So the same reaction and the next, so the reduction potentials in the next equation associated with this same reaction, so the one connected to the redox couple lithium plus and lithiums, is extremely low, around minus 3.05, this depends on the activities, the temperature and other parameters. But you can appreciate how much this reduction potential is low. And we know that how much is the difference between this potential and this one, basically the difference, it will be defined the final DDP. And since the oxide lithium electrode is associated with lithium oxide a certain potential that is quite close to 1, we can appreciate how the potential difference is huge. And when the battery is completely charged at full load, it could be even close to 4 volts. So we have a huge output voltage. And this is ensured due to the fact that we are able to intercalate lithiums inside this graphite support with an extremely low reduction potential. But why we are not using lithium as metallic lithium? So even lithium as metallic lithium, it could be used in order to achieve this potential, because lithium also in metallic state is obviously associated with this high reducing character. But the reasons for which we are using graphite and a lithium cation inside with respect to metal lithium is that metal lithium is used only for primary lithium batteries. Why? Because exactly in the case of zinc air battery or metal air battery, if we are using a complete metal zinc lithium electrode during the recharging process, we can have a bad redeposition with the formations of detritus and agglomerate and changes in morphology. And we can even create something that can break down the separations and cause short circuit. In order to understand these problems, the problem connected with the generations of aggregate and changes in morphology due to a recharging associated every time we have a completely metal electrode, is important to look at one of the first lessons about the metal air battery and zinc air battery. So we can see the links in the description. So basically, what you can say now is that the possibility to exploit an intercalation mechanism and the intercalation with respect to pure lithium electrode allow us to avoid changes in morphology, avoiding this agglomerate creation, and so we have something that is characterized with a significantly higher life, and we can promote more and more cycling of charge-discharge from 500 up to thousands, 3000 and even more in the most advantageous types of lithium-ion batteries. So basically the reasons for which we are exploiting graphite at the very beginning is this, because in this way we are able to solve a lot of problems concerning rechargeabilities. So the lithium is interesting because in this way we can have an output voltage that is huge. But the use of graphite leads to different sets of advantages. One advantage is the rechargeabilities, so better secondary direct battery are created due to the use of graphite, cause no bad deposition of lithium occurs. And another type of advantages connected to the graphite is that this is a cheap material. And so we are increasing the economical efficiency of these types of device. So this is what all for what concern this electrode. And then it's important to say that basically, since the lithium is not only a strong reducing agent, but is also lighter with respect to other types of devices, we are not only looking about something having a high voltage, but also a high specific energy. So we have a high specific energy. And the value of the specific energy in this case is from 150 up to 200 watt-hour per kilos. So quite big specific energy. Obviously it's not so bigger as in the case of metal air battery, since we have a little bit heavier device. Obviously we need to remember how interesting is the gas diffusion electrode in zinc air battery, in which basically we are saving a lot of weight. But with a comparison between this type of device and zinc air battery, what is interesting here is that we have, even in this case, a quite big specific energy, but an extremely higher output voltage. No other types of rechargeable devices are characterized with this huge DDP concerning these types of cell. So now it's important to say that there are a lot of advantages connecting lithium-ion batteries. But there are even some hazards and risks. And all these hazards and risks are connected with the use of lithium. Because lithium is a quite reactive alkali metal. It's an extremely reacting. It's also the use for which is so interesting for us. The reducing potential is so low since lithium in a classic atomic model is characterized with a single one electrons in the external shell. And since these electrons is present in the external shell, obviously this is a classic model, not a real quantistics model, but we are imagined to have one electron in the last shell, and obviously the tendency of this lithium to give these electrons away from it is huge. And so basically, since we know that the reduction potential is basically the tendency of one atom to release one electrons and to be oxidized in this way, obviously the tendency of these atoms to be oxidized is huge, since for which the reduction potential is so low. Obviously, for these reasons, the lithium is also a high reactive metal, an alkali metal, and is extremely reactive, for instance, in the case of interaction with water. When lithium reacts with water, we have the formations of lithium hydroxide and hydrogen. We have the release of with the release of energy, so A plus energy, and this can even cause some explosion. And this is the reason for which the electrolyte is never an aqueous electrolyte, but is an aprotic solvent in which a lithium salt is dissolved. We will see later this. And it's also important that this structure is completely sealed in order to avoid basically the contact with moisture. This is extremely important, because lithium basically starts to fire when it's in contact with water. So it's important to say that this concept can be well described also in according with the Purpet diagram of lithium. If we remember, for instance, the Purpet diagram of lithium, we have our potential here versus pH. We have the line of water, the oxygen reduction reaction, and the hydrogen reduction reaction. So water exists in this zone. Here we have these, and here we have the hydrogen zone. So we are from 0 to 1.23 volts with respect MHE. And concerning the reduction potential of the lithium's reduction, so this redox couple, we have defined how this is quite close to minus 0.5. It's really low, and obviously is independent of pH. We need to remember the nernst equation solution to understand this trend in the Purpet diagram. And what is important to say that here lithium exists as lithium 1 plus and here as metallic lithium. How we can say in the water range lithium exists only as lithium 1 plus, so it's not stable as metallic lithium. Reasons for which when we are placing metallic lithiums in water, this often is trying, not often, but always is trying to be oxidized in lithium 1 plus, and in this way we can have this reaction. So spontaneously the lithium reacts with water in order to pass from the metallic state to lithium plus. And this is the reason for which it's so quite reactive and we are not able to use water inside our electrolyte. And another hazard connected with lithium-ion batteries, together with the use of specific aprotic solvent and the use of a sealed structure, is also the fact that we need to avoid a too quickly recharging process, because a too quickly recharging process can even cause short circuit and promote an explosion. And if we are recharging the batteries too fast, or even if we are heating this battery on a temperature that is higher than 100 Celsius degree, we can promote the decompositions of the positive electrode, the compositions of the lithium oxide that can release water and even cause explosion. So the different steps of problem concerning lithium-ion batteries, even if we have a huge output voltage, we have a high energetics efficiency, and extremely high number of cycles for charging and discharging and use stability, the main problem are the hazards connected with lithiums with interactions with water. The possibility to generate short circuit if the recharging process is conducted in a bad way, push it too much on the finish or too quickly. we have a bad stability versus high temperature, and when we are approaching 100 Celsius degree, we can add even explosion due to the decompositions of lithium oxide and the release of oxygen. And we can even have problems connected with the cost, since these types of devices are quite expensive if compared with other types of batteries, as lead acid, zinc, air, and so on. So basically we have these types of interesting aspects. Now it's important to focus our attention on the structure of the electrolyte and before the structures of the lithium oxide. The lithium oxide, in this case, it could be different. We can have different types of lithium oxide. We can have maybe one of the most used is obviously lithium cobalt oxide, but we can even have lithium manganese oxide and lithium iron phosphate. We can have different types of oxide and even a mixture of them, so a mixed oxide. Why I'm using oxide here? Because the lithium, how said, is not stable as metallic lithium. We have a really low reduction potential, so we have a huge tendency to give electrons. And for the reason lithium is not stable, and they often try to undergo an oxidation. But when it's present inside a crystal lattice of an oxide, is stable. And is it stable, in this case, if we are able to freeze a situation in which lithium is taken at the very beginning in the graphite, since the lithium is try to enter inside the lithium oxide, this is due to the fact that if the lithium is stable inside the oxide, is stabilized in this crystal lattice, you want to achieve this state. And so if we are putting lithium as lithium zero due to the intercalations of lithium plus inside the graphite, we have, in the moment in which we are closing the circuit, this spontaneous tendency of lithium plus to ask from the graphite and try to reach the oxide lithium, and in this promoted the release of electrons that are collected here during discharge. Why? Because we know that when we are exploiting a galvanic cell, so we are exploiting a spontaneous reaction. And since we have the lithium is stable inside this crystalline oxide and not stable in graphite, it spontaneously tends, when we are closing the circuit, to promote the passage of lithium from this zone to this zone. And so during the discharging, we have the intercalations of lithium from the graphite and the intercalations of lithiums inside the lithium oxide. Because we are decreasing the free energy in this way, and by decreasing the free energy, we are increasing the electrical works. Obviously, when we are recharging with the battery, we need to provide the opposite process. And this means that we are passed from a stable state, lithium is stable inside the oxide, in a non-stable state, and so we need to provide energy with an electrolyzer. So basically, in a moment, I want to describe also from a reaction point of view, which are the intercalations mechanisms and the intercalation mechanisms of lithium inside these batteries. So we want to describe the galvanic cell and so the connected sim reaction associated. But what is important in this case is that we have a real intercalation and the intercalation process, and the intercalations from graphite and intercalations inside the oxide during discharge, and the opposite pathway during the recharging. So during discharge, lithium asks from the graphite and is entering inside the oxide, the decreasing basically with an oxidation process here and our reductions of the metal, not the lithium, is important. So here we have an oxidation of the lithium during this step. So the lithium passed from lithium zero intercalated as lithium plus with the release of electrons that we have in oxidation. And in this case, electrons are collected and we have intercalations of lithium. But in this case, what is reduced is not the lithium, because lithium is still remain as lithium 1 plus inside the oxide, because it's stable. But what is reduced in this case is the corresponding metal, cobalt, manganese, this one. What is important is also to say that these types of oxide is the best one, the cobalt, the lithium cobalt oxide, but nowadays we have a lot of problem concerning the fact that there still remain a pure amount of cobalt in the earth, and so the price is increasing. And it's also important to say that cobalt is used a lot of different applications, for instance in metallurgic applications for alloys, useful for instance in the use of the medicines. Chromium, cobalt, nickel alloys are used, for instance cobaltum, chromium, molybdenum alloys are, for instance, used in medicines for prosthesis application. And so we have that the price of cobaltum is increased, and different types of oxides should be studied in order to reach some performance that can be comparable. But nowadays, no other types of oxides is good as this one in order to provide the best final DDP and the best output voltage. So basically, we have this aspect. We have the fact that the lithium, cobaltum, and lithium-ion oxide and so on compose these electrodes. And what still remain now is, for instance, the types of electrolyte. In this case, the electrolyte we know it cannot be, for instance, water, an aqueous, a protic solvent. We need to introduce a protic solvent in which lithium salts are dissolved. So we can use, for instance, often some carbonate. We can use diethyl carbonate, or ethylene carbonate, or even propylene carbonate. So we are using organic solvent, a protic solvent, in which lithium salts are dissolved. And so these lithium salts are basically lithium cations complex. Has, for instance, inside the solvent we can have lithium hexafluorophosphate, we can have lithium tetrafluoroborate, and we can have lithium perchlorate. So different types of lithium salt, lithium cations complexes inside this organic solvent. So in this case we are creating an electrolyte that is not protic, and we cannot have the generations of hydrogen and explosion. So basically now we have described each single component of our cell. And in the next lesson, the second part regarding lithium-ion battery, we can focus our attention on the main problem concerning the degradations of the electrolyte, and so the self-discharge process, and the different steps of electrolyte, the future perspectives in terms of solid electrolyte and even aqueous electrolyte. This is quite strange, but is an interesting new research field. And also obviously the galvanic chain and the connective sim reaction to this process, concerning also the different types of feature that a solution should have and the salt should have.